On Lena's first solo night watch at the moon's south pole, two thermal lines begin to separate while 5 people sleep beyond a thin partition. One line may be lying. The other may be warning her that a margin is beginning to disappear. Tonight, in a grounded fictional journey made to help you sleep, we will stay beside her as the base waits for a decision. Which reading should she trust? What can she touch without creating a real fall? And how long can she investigate before responsibility requires waking the crew? You may let the questions drift. Lena will hold them for you. Lena has trained for this room, helped commission its systems, and imagined the pride of returning a perfectly ordinary watch to the next shift. Now she wants the simplest explanation so badly that she distrusts the wish itself. That it be only a sensor, she thinks. That the neat answer be the true one. Her hand hovers beside the controls, close enough to act and disciplined enough not to. Outside, the ridge remains dark beneath a black sky. Inside, fans carry every sleeping breath through ducts Lena cannot see from her chair. Pumps move heat toward radiators powdered with abrasive dust. Recovered water waits in closed loops. Batteries count down toward a cabin morning the sun will not announce. You may follow every quiet light, or let the numbers soften and drift away. Lena will keep the watch. I'm Elias, guiding your imagination through hidden history. In the comments, leave your next journey idea and one improvement. Upvote favorites. These episodes take many hours of research and editing. A like or subscription supports this small channel. If chosen, I'll credit your name. Now, step inside. The room belongs to Lena again. Green symbols move slowly across the display. The colder trace continues downward by a fraction, then holds. The second line refuses to follow it. Behind the closed doors, no one stirs. She could wait the duty systems lead and place the uncertainty in more experienced hands. She could call Earth and wait through the slight conversational delay for another engineer to see the same numbers. She could trust the colder sensor and change a valve. She could trust the calculated line and mark the sensor for replacement. Every choice carries a different cost, and none has earned her confidence. One small setting change might make the lines agree. That possibility is exactly what makes her pause. Agreement created by her own command would feel like relief, not proof. She draws her hand away from the controls and opens the outgoing watch node instead. Somewhere beyond the habitat wall, radiator panels face a darkness no human skin could enter unprotected. Somewhere much farther away, replacement hardware rests on Earth, close enough for conversation and impossibly far from tonight's workbench. Lena does not yet know whether she needs either one. She knows only that the next action must leave the mystery clearer than she found it. The outpost in this story is imagined, assembled from real constraints and technologies still being studied or developed. Its exact rooms, readings, and procedures belong to Lena's night. The vacuum, abrasive dust, delayed physical resupply, and need to account for power, heat, air, and water belong to the real problem of living on the moon. A lunar night may be cold while an occupied habitat is still trying to release heat. People, computers, pumps, fans, lights, and water processors all add warmth. Equipment near the outer shell may need protection from cold at the same time. The two traces therefore led into a system that can carry heat away from one place while guarding it in another. Lena cannot solve the disagreement by asking whether the moon is simply cold. She must discover which part of the balance has changed. One line comes from the normal temperature channel on a branch of the habitat's external thermal loop. The other is calculated from a second sensor and the expected heat load. In this imagined base, those measurements are intended to be independent enough that disagreement means something. But independence must be checked, not assumed. Two sensors can share a power supply, a wire route, a calibration reference, a software calculation, or even the same patch of metal. If they share the cause of an error, Two matching numbers may offer less reassurance than they appear to. The caution itself is only an invitation to look. An alert system is useful when it tells a worker what changed, how quickly it changed, and which functions might be affected. Acknowledging the caution does not erase the condition. It simply tells the system that a person has received it. In this fictional interface, Lena can leave the trend visible while reducing the chance that a repeated tone will become the loudest fact in the room. The work still depends on comparing the indication with the physical system. Lena opens a configuration history. She checks whether a pump changed speed, whether a valve received a command, whether a water processing cycle began early, and whether one of the habitat modules drew more power than forecast. A choice is observable in what she does not do. She does not silence the caution and forget it. She does not swing a valve to a new position merely to make the lines meet. An unnecessary correction could create a real change in a system that had only been measured badly. The fictional checklist asks first whether the crew is inside safe operating margins. The answer is yes. It asks whether a rapid trend is developing. The answer is no. It asks whether the suspect channel has an independent comparison. The answer is partly, which is not the same as fully. Lena begins a hypothesis ledger, a plain list of possible causes and the evidence that would make each one more or less likely. There could be an extra heat load. There could be reduced fluid flow. A valve could have stopped short of its commanded position. A radiator section could be rejecting slightly less heat than expected. A temperature sensor could be drifting. More than one small thing could be true at once. At the end of the outgoing watch, another technician had left a note about one exterior radiator sector after the last dust control cycle. The note did not call it a failure. It simply said that the sector had settled a little more slowly than its neighbors. That detail now enters Lena's ledger without being promoted to an answer. The two lines continue apart, slowly enough to study. The base remains quiet. Lena has not fixed anything, but she's prevented the first and easiest mistake, treating a reading as a diagnosis. Before she can understand the small difference on the screen, she must understand the long darkness around the base and why this particular night does not belong to every place on the moon. From inside the habitat, darkness can look simple. The exterior cameras show pale ground, a few hard-edged shadows, and the black sky beyond. Yet near the lunar south pole, night is shaped less like a blanket and more like a map. The familiar description of a lunar day often gives roughly 2 Earth weeks of light followed by roughly 2 weeks of darkness. That is a useful picture for some broad discussions, especially away from the poles. But it is not a schedule that can be assigned to every South Polar landing site. Near the pole, illumination depends on the exact point on the ground, the local hills and crater rims, the season, and the height of the object receiving the light. A solar array raised above the surface may see sunlight that a low instrument cannot. A ridge may remain bright, while a nearby hollow lies in shadow. This is why current lunar engineering studies treat illumination as a site-specific calculation. It is also why tall vertical solar arrays are being developed for polar use. They may reach low-angle sunlight and lift part of the collecting surface above nearby obstructions. They are proposed technology, however, not proof of the equipment installed at some future first base. In this story, the base occupies an unnamed ridge whose local horizon creates a planned shadow lasting several days. That duration is invented. The outpost's vertical arrays, batteries, and stored chemical energy are also story choices drawn from real development work. Lena is not surprised by the darkness. She confirms it against the site's horizon model because the model tells her what the power and thermal systems were expected to do. Low-angle polar light creates another problem when it is present. A sunlit surface can be glaringly bright beside a shadow with very little visible detail. The human eye, a helmet light, a window, a camera, and a display all become parts of the same visibility system. Tonight, most of that bright edge lies beyond the base's local horizon. The exterior cameras use their own controlled lighting, enough to reveal the nearest equipment without pretending that the whole landscape has become evenly visible. Visible darkness also does not supply a complete temperature map. A sunless surface, an insulated electronics box, a buried cable, a radiator, and the interior wall of an occupied habitat can all follow different thermal histories. Engineers use site measurements and models rather than one dramatic outside temperature. Lena therefore checks the thermal forecast by component and mode. She does not use the black sky as evidence that every exterior object must be cooling in the same way. Inside, the word night has a second meaning. The crew follows an internal schedule so that some people can sleep while a smaller watch monitors the outpost. Their clocks are not waiting for the sun to move above the ridge. Cabin morning will arrive according to human work and rest, even if the cameras still show darkness outside. The distance to Earth also has two meanings that are easy to mix together. A radio signal crosses the average Earth-Moon distance in about 1.3 seconds one way. Digital processing, routing, relay schedules, and ground operations can add delay, but a conversation with Earth is not delayed for days as it would be across interplanetary distance. When a usable link is present, specialists on Earth can answer within the rhythm of a slow conversation. What Earth cannot do is reach through the signal. It cannot place a hand on Lena's connector, see dust hidden behind a cover, or deliver a replacement module before her shift ends. A physical shipment requires suitable hardware, launch, transit, landing, and surface transport. So the phrase "Earth is days away," when it appears in this story, belongs to travel at best and to logistics more generally. Radio is close. Replacement hardware is not. Lena checks the local horizon forecast and the internal clock, then adds them to our open record. The base is in the shadow mode it was designed to enter. No unexpected sunrise or eclipse explains the trend. Cabin morning remains several work periods away, but her own handoff is much closer. The next question is stored in the power ledger. Every pump and fan that keeps the outpost habitable draws from it, and nearly every watt eventually becomes heat. If the ledger is wrong, the thermal discrepancy may be telling the truth in a language Lena has not yet translated. A lunar power system is not only a generator. It is a chain that begins with generation and continues through storage, switching, distribution, protection, and the loads that finally use the energy. A reliable source can still be defeated by a failed cable. A full battery can still be isolated by a protective switch. A healthy bus can still be asked to support more work than its reserve policy allows. The precise power system in this base is fiction. During illuminated periods, tall solar arrays charge batteries for brief changes in demand, and a regenerative fuel cell system for the longer planned shadow. A regenerative fuel cell stores energy through chemical reactions, and later converts that stored chemical energy back into electricity. NASA and its partners are developing such systems for sustained lunar operations, just as they are developing vertical arrays and fission surface power. No single one of those paths should be mistaken for a settled design of the first occupied base. This imagined outpost does not have a fission reactor. Its solar and stored energy system was chosen for the story because it makes the night's bookkeeping easy to follow. Essential loads occupy protected branches. Discretionary loads occupy others. The distinction is not that essential machines are always important and discretionary machines are frivolous. It means some work can move in time without endangering the crew. Reserve is also more than unused energy. Part of it covers forecast uncertainty. Part protects against a component that must run longer than planned. Part allows a bus to be isolated without leaving every essential load on the same path. A margin can be healthy even while energy is being consumed, provided the decline follows the planned envelope. Lena watches the shape of that decline not only the amount remaining at one moment. Ventilation, atmosphere monitoring, critical thermal pumps, control computers, emergency lighting, and minimum communications remain supported. A fabrication machine warming for a later job can wait. A rover battery that already holds sufficient reserve can wait. A waste processing cycle can be delayed if its contents are secured and the deferred work is given an owner. Lena reads the stored energy trend against the forecast for the base's invented shadow interval. The decline is close to plan. There is no sharp loss and no unexplained bus transfer. Still, she can use a reversible load change to learn something about the thermal discrepancy. She cancels the fabrication warm-up before it begins. She postpones the waste processing batch and records its new review time. Then she watches both the power curve and the two temperature trends. The total electrical load falls by a modest amount. A few minutes later, the rate of thermal separation slows. The change is modest enough to feel almost unsatisfying. At the start of the watch, Lena wanted an action that would end uncertainty. This action has a different virtue. It is permitted, recorded, and reversible. If it teaches her nothing, the next watch can still see exactly what she changed and why. For the first time since the line separated, she feels the problem acquire edges. The base is not becoming less safe while she studies it. She has not solved the disagreement, but she has made one part of it answer a controlled question. This is a small but useful answer. Some of the observed change came from an ordinary heat load. That does not mean the fabrication machine was faulty or that the waste system threatened the habitat. It means the model Lena was comparing against had assumed work that was now shifted in time. By changing a permitted load and observing the response, she has used conservation as a diagnostic tool. The separation does not disappear. One temperature channel still reports more heat than the power ledger can reasonably account for. That remaining difference matters because most electrical energy used inside a habitat eventually appears as heat somewhere. Computers transform electricity into calculations and heat. Motors transform it into motion and heat. Lights transform it into visible light and heat. Even useful work tends to join the thermal balance before long. Lena checks whether a protected bus and the suspect sensor share a power conditioner. They do not. She checks whether the sensor's data path passed through a software update during the previous watch. It did not. The power system is not cleared forever, but the most immediate common causes are removed from the ledger. The deferred tasks do not vanish when their switches turn off. Lena attaches an owner, a reason, and a revisit point to each one. This is part of keeping one small decision from becoming another shift's surprise. The waste batch remains sealed. The fabrication job remains queued. The stored energy margin improves by a small, predictable amount. Power is explained part of the heat, and only part. To understand what remains, Lena must follow the energy beyond the bus, through the loops that collected from the cabin and carry it toward the dark exterior. In vacuum, the final step is not a breeze or a cold draft. It is a surface releasing energy as radiation into space. On Earth, it is easy to associate cooling with moving air. A fan passes room air over a warm surface. Wind carries warmth from skin. Outdoor equipment gives heat to the atmosphere around it. On the moon outside the habitat, there is no surrounding air to carry that energy away. A radiator can still reject heat in vacuum, but it does so by emitting infrared radiation. Before heat reaches that surface, it must travel from the places where it was produced. Cabin air moves warmth away from people and equipment. Cold plates and heat exchangers collect it from electronics and other loads. Fluid loops carry it through the habitat. An external loop carries it toward radiator panels. The exact fluids and arrangements depend on the design. NASA studies of possible surface habitats examine internal and external loops, heat exchangers, radiators, thermal storage, insulation, heaters, and special modes for long darkness. They are conceptual architectures, not a public blueprint for a finished base. In this imagined outpost, two fluid loops meet through heat exchangers and feed several radiator sectors that can be observed and, within limits, reconfigured. The story does not need to invent coolant temperatures or valve thresholds to make that chain understandable. Some studies consider retracting radiator area, storing heat for later release, allowing selected temperatures to move within wider limits, or transferring heat between systems that need opposite things. Each option trades mass, power, moving parts, and control complexity. The useful fact is not that one option will certainly be chosen. It is that thermal design includes. Heat may be rejected now, stored briefly, or redirected, and the chosen mode must match the changing loads. The same system can face opposite demands. Electronics in an occupied module may need their waste heat moved away. A dormant exterior component may need insulation or a heater. A battery may need to stay within a narrow temperature band. A radiator that is useful while loads are high may become a path of unwanted heat loss when loads are low. Night is a changing balance among production, transport, rejection, storage, and protection. Lena begins at the internal side of the chain. She checks the commanded state of the pumps and compares it with their electrical current and measured flow. A pump that says it is running but draws no current would tell one story. A pump drawing current against a blocked path would tell another. Tonight the currents and flows are steady. She opens the valve history. No command arrived at the moment the trend began to separate. Each indicated position matches the command closely enough for the fictional procedure. She checks the pressure difference across the branch filter, then the temperature before and after the heat exchanger. The numbers do not suggest a gross restriction or a sudden loss of fluid. Next, she compares heat production with heat transport. The power ledger gives her an estimate of electrical heat. The crew schedule gives a quiet estimate of metabolic load. Water processing and communications add their expected shares. The normal temperature channel suggests that the loops are carrying approximately that amount. The suspect channel suggests more. This contradiction makes sensor drift more likely, but it does not clear the physical system. One exterior radiator sector still changes a little more slowly than its neighbors when Lena performs a small, permitted adjustment in load. The effect is much smaller than the suspect sensor claims. It is also consistent enough to remain on the ledger. Dust is one possible contributor. A layer on a radiator can change how the surface absorbs and emits energy. Peer-reviewed modeling supports that possibility under model Lunar conditions, but it does not provide a universal percentage that can be assigned to any future panel. The amount, distribution, surface coating, illumination, and temperature all matter. The store's radiator sector and its behavior remain invented. Lena does not send anyone outside. The habitat has alternate radiator capacity in this fictional architecture, and the measured conditions remain within margin. An exterior excursion during a dark watch would introduce far more dependencies than the small discrepancy justifies. Her ledger now separates 4 layers. Heat production changed little because of scheduled work. Heat transport appears steady. One measurement channel may be drifting. One radiator sector may have a smaller real change. The next task is to account for the machines that keep the cabin air clean, because they are both life support equipment and part of the thermal load. Life support is sometimes imagined as a single machine that makes oxygen. A real environmental control and life support system is a collection of functions. It maintains pressure. It moves air. It removes carbon dioxide and trace contaminants. It manages humidity. It supplies oxygen through generation or stored reserves. It detects fire and supports emergency response. It connects with water recovery and waste handling. Each function has its own hardware, and each has interfaces with power, heat, data, and crew time. The International Space Station has demonstrated many of these functions for years. Its equipment removes carbon dioxide with molecular sieves. It generates oxygen by splitting water through electrolysis. Sabatier chemistry can combine carbon dioxide and hydrogen to recover some water. Fans mix cabin air and move it through treatment equipment. Those are important pieces of heritage, but a lunar base may adapt them differently because gravity, dust, volume, mission duration, logistics, and maintenance are different. Monitoring must also distinguish the cabin from the equipment that serves it. A carbon dioxide sensor measures the air at its location. A fan current sensor reports motor behavior, not necessarily airflow in every corner. A pressure sensor can remain normal while a treatment cartridge approaches its service point. No single number describes breathable air by itself. The operator builds a picture from composition, pressure, movement, humidity, equipment state, and the agreement among locations. In this imagined habitat, the crew breathes air moved through several zones. Lena checks more than one carbon dioxide sensor, because a reading in one quiet corner may not represent the entire cabin. She checks fan current, commanded speed, and the pressure difference across a filter. She checks whether a hatch between compartments changed the path of circulation. The fan is turning as expected. The distributed sensors agree within their normal fictional tolerance. The filter has collected enough material to appear on the routine maintenance list, but its pressure difference is not rising quickly. A filter that grows dirty can make a fan work harder and can change airflow. It does not, by itself, consume the habitat's oxygen or open the pressure shell to space. This distinction is one of the quiet disciplines of systems work. A stopped fan, a carbon dioxide removal problem, an oxygen supply problem, and a pressure leak are different failure classes. They can interact, and they may share power or control, but they should not be collapsed into one vague idea that the air is failing. Lena compares the fan and processor heat with the thermal model. Both contribute approximately what the model expected. She checks the humidity load, because recovered moisture carries heat into the water system. It too remains steady. There is no evidence that the crew's atmosphere is beginning a chain reaction with the thermal discrepancy. The filter can wait for its scheduled service window when a clean work area and replacement element are prepared. Lena adds a note, not an alarm. She does not replace a functioning part in the middle of a separate diagnosis merely because it is available to touch. Beyond the partition, the sleeping crew remains represented on the displays only as gentle collective loads, a little warmth, a little moisture, carbon dioxide for the removal system, oxygen demand for the supply system. The script does not need exact cabin percentages or alarm limits. Those would depend on the chosen architecture and mission rules, and none is needed to understand the task. The air system gives Lena another local payoff. It is stable. Its normal heat has been counted. Its measurements do not support a wider cascade. Lena notices a little tension leave her shoulders. The crew beyond the partition is not sleeping through an expanding emergency. They are sleeping through a bounded watch problem that still deserves care. The remaining question moves with the captured humidity into the water recovery system, where almost every drop is valuable, but no percentage should be treated as magic. Water in a closed habitat seems to travel in circles. It begins in treated storage. A crew member drinks it. Some leaves the body as moisture in breath and perspiration. Some enters hygiene and waste streams. Humidity condenses at the air system. Urine enters a separate recovery path. Processors clean selected streams and return accepted water to storage. The circle is useful, but it is not perfect, and it is not self-explanatory. Water can remain tied up in filters, brine, waste, maintenance hardware, samples, or material awaiting processing. Equipment requires power. Pumps and processors add heat. Product water requires quality checks before it rejoins the accepted inventory. NASA reported a 98% total water recovery milestone on the International Space Station for a particular configuration that included a brine processor. That achievement shows how far recovery can go within a defined system boundary. It does not mean every future moon base will recycle exactly 98% of all water every day under every condition. The streams counted, crew load, equipment state, and definition of recovery all matter. Recovery is only useful when the product is acceptable. Conductivity, organic contamination, microbial control, and other quality measures may require sampling or continuous monitoring depending on the design. The story does not invent those limits. It gives Lena a simpler operational distinction. Water is either in accepted storage, held for a test, moving through a known process, or tied up elsewhere in the inventory. That distinction lets a questionable batch be isolated without turning every tank into the same problem. In this fictional base, the water system borrows functions from ISS heritage but keeps treated storage and an independent reserve. A questionable batch can be isolated and reprocessed, while the crew draws from accepted inventory. When paused processor does not instantly leave the habitat dry. Lena checks the batch log. The current recovery cycle began at its scheduled time and drew the expected power. Its pump current is steady. The product quality status remains accepted. Tank trends agree with the volume expected to move through the system. There is no hidden early start that would account for the suspect thermal channel. The waste processing batch she deferred in the power chapter remains secured. Delaying it creates work for later and keeps some recoverable water tied up longer, but it does not create an immediate sanitation or life support emergency. Lena records the delay beside the power reason and the new review time. Material does not disappear merely because a switch is off, and responsibility should not disappear either. Current Lunar programs also study in situ resource utilization, finding, collecting, and processing local materials. Water ice near the lunar poles and oxygen-bound and regolith are important possibilities. Instruments have measured lunar resources, and reactor concepts have processed simulant. Those facts do not establish routine production of potable water for an occupied base. Extraction would still need energy, machinery, storage, purification, testing, and a sufficiently characterized deposit. For that reason, this story's early base does not depend on mined lunar water to keep the crew alive. It may host small resource experiments at another time, but its night inventory comes from supplies and recovery. This is a fictional design choice, made visible rather than smuggled into the story as a prediction. With the water and waste loads accounted for, Lena returns to the heat balance. Expected electrical use, crew load, air treatment, humidity recovery, and water processing now agree with the normal sensor. The suspect channel still reports too much. The remaining physical difference is much smaller. One radiator sector takes a little longer to respond. The story has reached a useful narrowing. Air is stable. Water is stable. Waste is deferred safely. Stored energy remains on plan. Fluid flow appears steady. The discrepancy is no longer an undefined threat moving through every system. It is a measurement question paired with one bounded exterior effect. Lena's wish for a simple sensor fault has not vanished, but it has changed. She no longer needs the wish to be true. She needs the independent reference, the load response, and the radiator behavior to agree about what each can prove. Lena brings the independent calibration reference to the console. Before she declares an answer, she will ask the sensor, the power ledger, and the radiator response to tell the same story twice. The calibration reference is not a magic truth machine. It is another instrument with its own history, certification, and limits. Its value comes from being maintained separately enough to challenge the suspect channel. In this imagined base, Lena can connect it at a protected reference point without opening a fluid line or disturbing the pressure shell. She begins with the system in its conservative configuration. The deferred loads remain off. Alternate radiator sectors hold the required heat rejection margin. She records the current state so that every later movement can be compared with a known starting point. The reference sensor settles near the normal channel. The suspect channel remains higher. Lena waits through the time specified by the fictional procedure, then repeats the comparison. The pattern returns. Next, she restores one small, permitted electrical load for a short diagnostic interval. The power ledger rises by the expected amount. The normal channel and the reference respond together after the expected delay. The suspect channel responds too, but it begins from its displaced value. When the load is removed, the three trends fall and the same offset remains. This is strong evidence of calibration drift in the suspect sensing channel. It does not mean the physical radiator difference was imaginary. Lena compares the sectors during the same load change. One still settles more slowly than the others, though by a much smaller amount than the drifting sensor had implied. She opens the dust control record. Selected surfaces on this fictional base use an electrodynamic dust shield, a technology that applies electrical forces to move particles. A real EDS demonstration flew on Firefly Aerospace's Blue Ghost Mission 1 in 2025 and removed regolith from selected glass and thermal radiator surfaces. That was an important lunar demonstration. It did not prove that every future radiator, suit joint, floor, seal, or lung can be kept dust-free. The story's radiator sector completed its last EDS cycle but settled slowly afterward, just as the outgoing note reported. Dust may remain on part of the surface, or the sector may differ for another ordinary reason. The remote evidence cannot tell Lena exactly what is present behind every edge and cover. A later exterior inspection can answer that under an approved work window. Before recording the diagnosis, Lena pauses over the core control for the duty systems lead. At the beginning of the watch, her pride wanted to keep everyone asleep until she could offer a neat conclusion. Now she has the answer she hoped for, but not the whole answer. The sensor evidence is strong, and the smaller radiator effect is still real. If she waits for every uncertainty to disappear, one tired person will be certifying her own work. The more trustworthy boundary is here, after independent evidence, before a life support measurement channel is returned to service. Asking for help will not make the watch less hers. It will make the conclusion reviewable. Lena wakes the duty systems lead. This is not a dramatic summons. It is a planned use of a second responsible person. Together, they review the independent reference, the reversible load test, the heat balance, and the radiator sector response. The conclusion is deliberately divided. Most of the apparent thermal rise comes from a drifting sensing channel. A smaller real change remains in one heat rejection sector. The rest of the base is stable. Power, air, water, and fluid flow have not joined a cascade. Alternate radiator capacity keeps the outpost inside its imagined margin. Relief arrives differently than Lena expected. It does not come from being told that her first guess was right, because it was only partly right. It comes from hearing another trained person question the record and accept the same bounded conclusion. A judgment has not become smaller by being shared. Two ordinary causes can be harder to recognize than one dramatic cause. If Lena had blamed only the sensor, she might have erased the evidence of the slower radiator sector. If she had blamed only dust, she might have accepted a misleading measurement and sent a crew outside for the wrong reason. The energy balance and the independent reference allow both small truths to remain visible. The result is less theatrical than a single hidden defect and more useful to the next technician. This is the main practical answer, delivered while much of the night still remains. The base was never one failing machine away from sudden silence. It was a group of connected systems offering evidence, barriers, and choices. Lena's task was to prevent connection from becoming confusion. From here, the pressure of the night can begin to fall. What remains is qualified repair, clean boundaries, inventory, outside review, and a handoff slow enough for another person to question. The central uncertainty has become a set of ordinary tasks. She places the thermo branch in the conservative configuration accepted by the duty lead. The suspect's sensing module is now eligible for qualified replacement. The radiator sector is not. Its exterior work requires planning, lighting, dust controls, suit support, and a reason proportionate to the risk. It can wait. The relief in the room is small enough to see only in procedure. Lena closes several hypotheses on the ledger. The duty lead accepts the bounded finding. No one says the base has been saved. The outpost has remained habitable throughout, and the remaining work is ordinary enough to be scheduled. Dust is now a contributor rather than a villain. Before Lena replaces the sensing module, she will make sure the clean side of the habitat remains clean, and that the story does not turn one difficult material into a universal explanation for everything on the moon. Lunar dust is often described with dramatic words, but its quieter properties are sufficient to make it a serious engineering problem. It is fine. It adheres to surfaces. It can carry electrical charge. It is abrasive. It can interfere with seals, mechanisms, optical surfaces, radiators, suit materials, sensors, and filters. Returned lunar material and Apollo experience provide direct evidence of dust behavior, while later laboratory work and engineering studies explore its effects. Health researchers treat exposure as a plausible respiratory eye, skin, and performance risk. The exact long-term outcome for a crew living on the moon remains uncertain. Simulants used on Earth do not reproduce every property of returned lunar dust. It is responsible to call dust a hazard without inventing a disease for Lena or claiming that every grain is instantly poisonous. The best control is layered. Keep as much dust as possible outside the clean volume. Design surfaces and connectors to tolerate what enters. Capture particles at boundaries. Protect sensitive mechanisms. Replace filters. Clean deliberately. Monitor what changes. Use active methods such as EDS on selected surfaces where they are suited to the job. The layers also protect one task from another. A suit service area can remain dirty enough to do its work, while the sensor bench stays clean enough for connectors and references. A loaded filter can be sealed before it crosses into storage. A tool used outside can have a documented cleaning path instead of being declared permanently contaminated or casually carried everywhere. The point is controlled movement, not an impossible promise that the moon can be kept out entirely. In this imagined base, the dirty vestibule sits between surface equipment and the main habitat. Covered tools remain on its outer side until cleaned. Suit interfaces are inspected there. Air passes through replaceable filters before joining the protected interior flow. The arrangement reduces migration. It does not promise zero dust. Lena services the interior filter that appeared earlier on the routine list. This is not the exterior radiator repair. It is a contained maintenance task with a prepared replacement element, a capture cover, and a clean work surface. She confirms the fan path, isolates the filter housing according to the fictional procedure, removes the loaded element, seals it, and installs the replacement. The pressure difference across the housing returns to its expected range. Airflow remains steady. Lena inspects the clean side seal and records the old filter's identity. There is no shower of particles and no need for a sharp sound or sudden motion. The work is small, tactile, and complete. The exterior radiator sector remains visible only through its telemetry and camera view. Lena does not pretend that an image can reveal every thin deposit. She schedules an inspection for a later approved window with the EDS record, thermal trend, lighting needs, and alternate capacity attached. The task has prerequisites and a stop condition. That makes it safer for the worker who will inherit it. Earlier, leaving an open item might have felt like an incomplete first watch. Now Lena can see the refusing unnecessary exterior work as part of the repair. She does not need every thread to end in her own hands. Dust has now paid its part of the story. It can plausibly reduce performance and raise maintenance burden. It is not proof of the sensing error. It is not a force that defeats every barrier at once. The base remains a place where contamination is expected, measured and handed from one controlled zone to another. Lena packages the sensor comparisons and radiator response for Earth review. The next relay interval is not yet open, so the packet enters a queue. The moon is close enough for a conversation and far enough that local hands must still perform the work. A lunar communication system may use several paths. A surface antenna can speak directly to Earth when geometry permits. A relay in lunar orbit can carry the signal when terrain or orientation blocks the direct view. Local radios can connect habitats, vehicles, suits, and instruments. Each path depends on power, antennas, schedules, compatible standards, and a line of sight that the lunar landscape can easily interrupt. LunarNet is a real interoperability framework intended to help different lunar networks and services work together. ESA's Moonlight program and NASA relay studies describe future communications and navigation infrastructure. They are plans, specifications, and developing systems, not evidence that every point near the lunar South Pole already has uninterrupted service. This fictional base uses a direct path and a relay path. It also uses a store and forward method, so a complete packet can wait until a usable route becomes available. During the plan relay gap, Lena still has local control. The queued packet contains the trend history, the reference comparison, the load test, the current configuration, and the question she wants Earth specialists to review. At roughly 1.3 seconds one way, before additional operational delays, Earth is close enough to advise. Yet advice cannot turn a fastener, inspect a seal, or move a spare from a drawer. The most credible local repairs are therefore modest and planned. Clean a mating surface, reseat a connector, recalibrate an instrument, replace a filter, swap a qualified module, isolate a branch, or place a subsystem in a reduced capability mode. Additive manufacturing can help within limits. The International Space Station has demonstrated printing selected polymer tools and parts. NASA is developing broader on-demand manufacturing for polymers, metals, and electronics, together with the inspection needed to trust what a machine produces. Feedstock, energy, material properties, dimensional checks, and part criticality still matter. A printer is not a box that can make any missing object. Choosing what to carry is therefore part of repair long before a failure occurs. Designers look for common modules, predictable wear items, filters, seals, connectors, tools, and components whose absence would remove too much capability. They also accept that no manifest can contain every possible part. Maintenance studies use probabilistic failure data and experience from places such as ISS, but a lunar habitat will create its own pattern of work. Crew time, access, diagnosis, and testing can be as important as the mass of the spare itself. Lena's sensing module is a qualified line-replaceable unit carried in the base's spares inventory. That inventory is fictional, as is the maintenance authorization. She verifies the part number and calibration status with the duty lead. The lead does not take the task from her. A second set of eyes follows the isolation, part identity, and test plan. Lena powers down only the affected measurement channel, confirms that the independent channel remains available, opens the protected enclosure, and removes the drifting module. The connector receives a visual inspection. The mating surface is clean. The replacement seats without force. Lena closes the enclosure, restores the channel, and waits while it stabilizes beside the reference. The two readings agree. She repeats the permitted load test on a smaller scale. They rise together and settle together. For a moment, Lena feels the clean satisfaction she wanted at the start of the watch. The difference is that she no longer mistakes one completed repair for the whole truth. The module swap has repaired the measurement path, not the radiator sector, and her log says so plainly. The small fabrication station does have a role tonight, but not a miraculous one. From an approved file and known polymer feedstock, it makes a low criticality clip for the dust cover used during future service. The clip holds no pressure, controls no oxygen, closes no suit, and carries no claim that a printed part can replace a certified valve or electronic assembly. Lena measures it before placing it with the planned exterior work package. The relay window opens. The queued evidence reaches Earth, and an acknowledgement returns after the network and processing delay. The specialist can examine the same record while the base continues locally. No reply is required to keep the crew safe tonight, because the qualified repair has passed its fictional test and the physical radiator change remains bounded. Lena adds old and new module identities, test results, deferred tasks, and the open radiator question to the handoff record. Local repair is not meant independence from everyone else. It is meant knowing which action can be completed with present tools, which finding deserves outside review, and which task must wait for the right conditions. With the main system stable, she can use the remaining watch for a contingency check. The nearest vehicle is useful, but its usefulness depends on a distinction that future lunar stories can easily blur. A rover is not automatically a shelter. NASA's Lunar Terrain Vehicle work describes an unpressurized vehicle intended to carry crew and equipment farther across the surface. A separate NASA JAXA effort describes a future pressurized rover that could serve as a mobile habitat for extended traverses. Those are different capabilities. An unpressurized vehicle does not become a shirt-sleeve refuge simply because it has wheels and batteries. NASA engineers have also studied lunar safe haven concepts for hazards such as radiation, thermal extremes, micrometeoroids, and dust. A safe haven is defined by the hazards it protects against and the resources it can supply. A radiation shelter may not have independent life support. A pressurized rover may share software, charging, consumables, or maintenance dependencies with the habitat. A protected room cannot replace water that has been physically lost. Independence is most valuable when it survives the event that made it necessary. A shelter powered through the same damage switch would not be independent for that failure. A rover parked behind an obstructed route might be available in inventory and unavailable in practice. Water, food, batteries, communications, access, and thermal control each have a duration and a boundary. A readiness check asks about those boundaries before anyone needs them. The precise contingency in this story is invented. The base has an unpressurized terrain vehicle for mobility and an internal shielded room with a limited independent atmosphere supply, communications path, water, and power connection. A pressurized rover is planned for a later phase of the fictional settlement, but is not present tonight. No convenient escape vehicle waits outside the airlock. Lena's check is scheduled rather than triggered by danger. She follows the clear access route to the internal safe room. Markings remain visible under reduced lighting. The door path is unobstructed. Stored supplies match the ledger except for one non-critical item used during a previous drill. The independent communication unit completes its self-test. The local power connection is available, and the limited internal reserve shows its normal readiness state. She also asks what the room shares with the habitat. It occupies the same site. It depends on part of the same structural shell. Some data passes through common software. Its long-term survival still depends on the base's larger stores. These common causes do not make the room useless. They define what it can and cannot be trusted to do. The terrain vehicle receives a separate readiness notation. It can move suited crew and equipment. It can support a medical evacuation within the site's operational plan. It cannot shelter unsuited people, and its range depends on charge, terrain, lighting, navigation, and a route back. Lena does not call it an escape pod. The missing non-critical shelter item becomes a logistics task for the incoming watch. It has a name, a quantity, and a location. Nothing is replenished by optimism. Nothing is treated as urgent when it is not. The check widens the meaning of habitability. Keeping the base alive includes ordinary operation, fault isolation, and the preservation of options. It also includes knowing when an option does not apply. Tonight, no one enters the shelter for protection, and no one drives into the dark. The value lies in discovering a small inventory gap during calm conditions. The last major system of the night is not a machine. It is the human schedule that prevents one tired person from becoming the only place where important context is stored. Lena's watch must end, and ending it well requires more than leaving a written note. Human performance is part of spacecraft design. NASA's human system standards address sleep opportunity, circadian timing, workload, lighting, noise, temperature, displays, alarms, procedures, and the timing of demanding tasks. A base cannot treat fatigue as a private weakness and still claim to be engineered for people. Lena's shift length, roster, and briefing procedure are fictional. The principles are not. Workload should remain manageable. Critical work should not be scheduled casually at the body's lowest point. Lighting can support the crew's internal clock. A person who has reached a limit needs a clear way to pause, call another crew member, or transfer responsibility. The duty systems leave returns to rest after the sensing module passes its test. Lena prepares the incoming watch's briefing while there is still time to organize it. She does not rely on memory alone. Research on handovers and safety-critical work has found that written notes can be strengthened by direct, audio, or video communication. A NASA Ames-linked experiment found fewer errors in its simulated task when written information was supported by richer handover modes. That does not prescribe the exact checklist used on a future moon base. It supports a simple idea. The next worker benefits from both a durable record and a chance to ask questions. Fatigue makes that combination more important. A tired worker may remember the major event and omit the small configuration change that shapes it. A written record preserves sequence and identity. A direct briefing lets the receiver test the meaning, notice some ambiguity, and repeat the critical state back. Neither method is flawless. Used together, they reduce the amount of safety that depends on one person's working memory near the end of a watch. The incoming maintenance technician arrives at the system's console during an overlap period. The story does not give this person a name or biography because the role is what matters here. At the beginning of the shift, Lena imagined that earning trust might mean handing over no uncertainty at all. Now she understands a more demanding form of trust. The next person must be able to see what she knows, what she changed, what she left alone, and where her conclusion may still be revised. She begins with the current configuration, not the history of every thought that led to it. The alternate radiator sectors are carrying the required load. One exterior sector responds slowly and awaits an approved inspection window. The drifting sensing module has been removed. The replacement agrees with the independent reference and has passed a reversible load test. Earth has received the evidence packet. The deferred waste processing batch remains sealed and has a review time. The fabrication warm-up remains queued. The interior filter has been replaced and logged. One non-critical shelter item needs replenishment. Then Lena names the uncertainty. Dust may contribute to the radiator sector's slower response, but the remote evidence does not prove how much dust is present or whether dust is the only cause. The exterior inspection must be allowed to change that conclusion. She names the next checks and the triggers for waking the duty lead. The exact thresholds belong to the fictional base and are not spoken as real NASA procedure. What matters is that the incoming technician knows which trend to watch, when to watch it, what configuration should remain unchanged, and what observation would require escalation. The incoming technician repeats the critical configuration back. A question about the sensor reference leads Lena to show the test record. A question about stored energy leads to the deferred load list. Responsibility passes not when Lena stops speaking, but when the next person demonstrates that the system, its limits, and its unfinished work have been understood. This closes the opening questions in a quiet way. The thermal discrepancy has been separated into measurement and physical effects. The linked systems have remained inside their barriers. Local repair has restored the qualified measurement path without pretending to fix the exterior. The remaining work no longer depends on Lena staying awake to remember it. She signs the watch record. The incoming technician accepts it. Lena feels a quiet pride that does not depend on praise. Her first solo watch is ending with the uncertainty smaller, the evidence stronger, and another responsible person able to continue without borrowing her memory. The base is not perfect because no maintained place is ever finished. It is stable, legible, and owned by someone who is now alert enough to continue. Outside, the ridge remains dark. Inside, the lighting system has begun to prepare the habitat for a kind of morning that belongs to the crew rather than the horizon. The first change is almost too gradual to notice. A warmer tone enters the corridor lighting. The system's console remains dim enough for the incoming watch, while the path toward the sleeping compartments grows gently easier to see. This is Cabin Dawn, an invented lighting schedule guided by real concern for circadian rhythm and protected sleep. It does not mean the sun has risen beyond the local ridge. The exterior cameras still show the same pale ground and long darkness. Human morning and lunar illumination are allowed to be different clocks. Lena performs no last-minute repair. A final dramatic action would make the handoff less complete, not more. She returns the calibration reference to its protected case. She cleans the work surface. The removed sensing module remains labeled for later analysis. The approved dust-covered clip waits with the exterior work package. Each object has a place because each task has reached the point where another responsible person can continue it. The ventilation remains steady. Water continues through its accepted path. The waste batch waits securely for its rescheduled cycle. Stored energy follows the shadow forecast. The radiator sector gives away slightly less heat than its neighbors, and the alternate capacity carries the difference without complaint or ceremony. At the console, the incoming technician makes the first routine notation of the new watch. It echoes the note Lena inherited at the beginning of the night, but it contains more evidence. The slow sector is no longer merely an odd response. It has a known relationship to the repaired sensor, a conservative configuration, an inspection plan, and a list of conditions under which that plan should change. This is what the night shift is kept alive. Not only air, water, power, and heat, though all of those matter. It has preserved the base's ability to understand itself. A reading can be trusted or challenged. A margin can be seen. A task can wait without being forgotten. A person can sleep because another person has accepted the watch. A first lunar settlement, if it is built in anything like this form, will not remain habitable because every machine is flawless. It will remain habitable through layers, sound design, useful reserves, independent measurements, qualified spares, clean boundaries, modest repairs, honest uncertainty, and people who know when their part of the work is complete. Lena reaches the corridor and no longer turns to check the trend behind her. That is the small observable sign of relief the story permits. Earlier, pride asked her to hold the whole answer alone. Now it allows her to leave because the duty lead tested the conclusion and the incoming watch accepted what remains. She has not saved humanity. She has completed one watch, protected the next person's choices, and left one exterior task for the conditions it deserves. Beyond the wall, the lunar night continues according to hills, craters, and the slow geometry of the sun. Inside, cabin morning settles across closed doors, covered tools, and the low-moving air. You do not need to carry any of the remaining details. The log holds them. The incoming watch holds them. The base continues in its imagined darkness, one quiet handoff at a time.